Well, I did my PhD in the University of Amsterdam. I did theoretical physics, strongly correlated systems. And then I went to Innsbruck. I did my postdoc in Innsbruck and in the group working, among other things, on quantum computing, both on the algorithms and on practical implementation of quantum computation. Then I turned to biology and to biology of aging more specifically, and set up a company here that is working on analyzing large data sets of human data in order to build models of human aging and chronic diseases with the idea to find drugs that could help people control chronic diseases and aging itself. It's quite a turn, but since let's say my first love was among quantum computation, so obviously I'm talking and working sometimes with people from my previous life. And since quantum computation is developing pretty quickly over the last years, it's always important to see what this technology can bring to the table in practical terms, like drug discovery. So due to these, let's say, historical connections that I have to that field, I tried those waters a few years ago with the idea to see how mature is this technology. So basically, when I was doing physics, I was mostly interested in fundamental things, how to build quantum computers, how to make them working. Now, all this happens without me. So now I'm on the other side of the table. I'm interested if those things can be now used. And I think we are approaching the point where things are going to get useful. And of course, I want to be among the first people to learn when this actually happens. So that's why I'm interested in practical applications of quantum computing. Well, quantum computing is a way of computing that is using quantum systems like qubits in order to perform calculations. So life is infinitely richer than things that can be simulated with classical computers. So universe is quantum, all small things in universe are quantum, and quantum mechanics requires much more complexity in order to be not only understood but also simulated by computational devices. So we are classical creatures, and we humans don't operate in quantum realms, but our technologies operate in the realm of quantum mechanics. So that's why people study quantum mechanics. And drug discovery is a very interesting field. People may be surprised to understand that although we are totally classical objects, human beings, we are built of cells and molecules. Cells are still classical objects, but molecules are not. You cannot describe molecules without quantum mechanics. And now the most interesting thing, as engineers, we're using molecules to modify behavior of cells and tissues and creatures. So our instruments are quantum, molecules. They interact with other quantum systems like biological molecules. And we are waiting for these interactions to propagate to levels up from the hierarchy of complexity and change chronic diseases and aging. So that's why if you don't understand the root, like interactions of quantum objects, you don't understand at the end of the day what you are doing. So this is one of the reasons why drug discovery is so challenging. It's like doing things on one level of complexity and scales and nature and expecting results on the other. So that's why you have to have either lots of luck, so lots of drug design is still done by lots of trials and errors. This is one way of approaching complexity, which is working. It's just is a very resource consuming, and this is one of the reasons why making a novel drug is so expensive. Or you can expect that by taking knowledge from quantum mechanics into the drug design, by packing this knowledge with the help of quantum computing devices, you may hope that you can reduce this number of trial and errors that is required to actually connect the dots between quantum molecules and classical cells, tissues, and creatures, like we are, between chemistry and medicine, essentially. Well, I think the small summary is this, is that if you think about how many drug-like molecules could be there, out there, I mean, nobody knows, lots of them. And maybe 10 millions of molecules were synthesized by humanity as a whole. So it's a small fraction of all possible molecules. So among those non-synthesized molecules are all future drugs. But the total number of those things is so large that you need to have good ways to navigate in that huge chemical space. So you should be able somehow to go there and pick up molecules that look like drugs, although they have never been yet synthesized. They should look like drugs, have certain properties of drugs, and they should also exist, meaning that there should be ways to synthesize them, possibly at industrial scale. So in order to select for those molecules and try them in future experiments, you need to ways to generate those molecules. And not only all possible molecules that you can write, but only those which you can synthesize and that look like drugs and everything else. So you need to find good algorithms that somehow know which molecules exist, which molecules do not exist, and which of those molecules could be drugs. So this is one of the problems for generative artificial intelligence, which is very hot these days. It's like you're making texts or pictures. So these systems are taking all the texts that are already written and all the pictures that are already produced, and instead of memorizing them, they try to learn the rules, how good-looking pictures are created and how nicely polished texts are created. And then the systems could be run in generative mode, and they start producing wonderful texts and beautiful pictures. So we're attempting to do the same in this huge realm of molecules. We feed the systems with all molecules that were synthesized and are known to be biologically active. And we are making these systems to learn, as I said, not to memorize them, but try to understand the rules. What are the rules of chemistry that are making certain molecules possible and certain molecules not possible, certain molecules chemically active, biologically active, and certain molecules not. And if this system works, then it can be run in generative mode, and then instead of wonderful pictures, it starts generating hopefully wonderful molecules. The only problem is that the rules that are defining texts are the rules of classical mechanics, of classical engineering, whereas the rules that are defining good and synthesizable molecules are rules of quantum mechanics. So that's why the idea was to use a quantum device for the generative part of the algorithm. So we hired a D-Wave quantum annealer, off-the-shelf, commercially available quantum hardware, in order to do the generative work for us, as a kind of source of inspiration to make the system. So a quantum device could dream quantum dreams, essentially. So it can generate sophisticated distributions, out of which a classical, so that's why it's called hybrid system. So we have a quantum device that is dreaming quantum dreams for us. And then there is another classical network, classical AI, that is interfacing with the quantum device and tries to translate these sophisticated distributions of numbers that is generated by quantum device into molecules. So we train the system in parallel so that the quantum device is trying to do the quantum job and the classical device is trying to understand the results of the quantum device. And they work together in such a way that they start out with molecules. So they're trained with the existing molecules as image generation or text generation, and they output molecules that have never been thought of, because as I said, most of the molecules have not yet even been envisioned by anyone. So they start generate totally new molecules, and then we checked that on average they have properties that are expected from biologically active molecules, and they also have high scores suggesting that they are possible to synthesize. So in a way, we trained a hybrid system to generate novel molecules for us that look nice and could be seeds for future drug discovery programs. Yeah, sure. So the importance is this, is that quantum computation, as I said, is developing pretty quickly. But I think most of the people still think that this is a toy for quantum computation for the sake of quantum computing research. So people are measuring who is entangling more qubits, who has a larger computer. People are trying to solve very complex problems to show what is called quantum supremacy. But most of the time, those problems are not those problems that you would know about. I mean, some ultra sophisticated problem that cannot be solved by a classical computer, but so what? I mean, nobody cares about those. I mean, I'm not no disrespect, but most of the time, this is really a show of force of quantum computational technology. What I think we are approaching right now is the situation where where quantum computation could be actually used for practical problems. And obviously, it's still in its infancy. Quantum computers are still small, but we were able to demonstrate with the hardware you have already. You can fit hybrid algorithms into that small hardware in such a way that they start doing something useful, which means that we're approaching the inflection point. So let's say plus 5 years from now, quantum computers would be larger, which means that they would not be able just to fit a problem that looks useful, but already would start demonstrate solutions that are better than classical counterparts. So I think one of the goals of our work was to signal to everybody that although, I mean, to be fair, we cannot tell you that the system that we built is actually better than the classical system right now. But it's already working at the scale that is expected from the classical system, which means that in 5 years it will most probably be better than the classical system. Which means that our work should be a signal for people in drug discovery field, suggesting that these systems approach the level of feasibility. And as we know in technology, this level is very quickly surpassed by the situation when they are superb. So we're basically inviting everyone to look at algorithms from the drug discovery realm in quantum computation, pay attention to the developments in quantum computation, and see maybe for everyone that's their, let's say, choice where to jump in, when to jump in. We believe that we're at the inflection point, so people should start pay attention to that, and we believe that our algorithm will be very quickly surpassed by more efficient algorithms. Now, with respect to aging, well, aging is a complex problem on its own. We believe that aging in humans can be solved only by analyzing lots of data. Fortunately, we are living in the best of worlds, in the best of times, because we have lots of data from humans, we have lots of genetics, electronic medical records, everything. That's why we need to develop machine learning solutions that are able to understand this data. And there is a very big role played by generative algorithms in this. So that's why we are looking for ways to build better generative algorithms. And quantum computation may be a way to go. So we started with a problem that everyone understands how to solve, like this generative chemistry. And we are keeping our hands on this technology, and we're thinking how actually use it with much larger data sets that include health data from humans. Well, at the heart, we are analyzing progression of diseases from large human data, aging and diseases. The uniqueness of our approach is that age is the most important risk factor of any chronic disease. It's much larger than smoking and everything else. You need to be old to get diseases of old age. So we look at human health as a dynamic process. We bring lots of intuition and methodology from physics. We are building physics-informed machine learning systems that are actually interpretable, and they it's like weather prediction or financial market prediction. So we want to bring this level of understanding of dynamics of human health into medicine in order to understand which factors are contributing to different chronic diseases. We believe that this is the point where machine learning can do most for drug discovery. And of course, at the end of the day, aging is probably one of the most interesting and complex problems in medicine. And when we are facing this level of complexity, no amount of technology is good enough. So that's why we are looking for all kinds of improvements in modern machine learning, either classical or quantum. We just feel like solving aging requires the fusion of all possible technologies. The mere fact that aging has not yet been solved implies that there should be a few more technologies to get developed before this problem is getting solved. And we're trying to acquire the necessary bits and pieces to make sure that the problem is resolved. A number of companies are trying to include quantum computation into drug discovery. As I said, you cannot do drug discovery without understanding quantum mechanics. Quantum mechanics is known from, let's say, Pulp Fiction to be somewhat complex. So that's why artificial intelligence should be able to help, like a translator, between the complexity of quantum mechanics and desires of, brick and mortar technologies, including medicine. So I think that all the technologies develop somehow, all the necessary technologies that need to revolutionize the drug discovery from trial and errors to rational, some kind of rational engineering are developing together. And quantum computing, as I said, is just a necessary piece, unless we are trying to solve diseases with molecules. We need to have technological solutions for quantum complexity, and that's why I think this will necessarily be a part of future medicine and drug design. Quantum computation will be necessarily a part of future drug design and medicine.